Here we are with Unit 5, Lesson 2, Introduction to Functions. We're going to learn a little bit more about what a function is today. And we're going to start that off by comparing a list of numbers with another list that we're going to make. So here's our first list of numbers. It's 1, -3, -2, 3, 2, 1/4, and 5/10. So how many different numbers are actually listed? When we count them up, we find that there are 7 different numbers. When we make a new list containing the squares of these numbers, what we will see is something that's a little bit different. So when we talk about a square, I'm just going to make a table so that we can show all these. When we talk about a square, we're talking about a number multiplied by itself. So if we're talking about any number n, this simply means just n times n. It's the product of the number multiplied by itself. When we square 1, we get 1. -3 is 9. -1/2 is going to be a positive 1/4. And these two, both of them, because it's a negative times a negative. 3 squared is 9. 2 squared is 4. 1/4 squared is 1/16. And 5/10 squared is 25/100. And so the next question asks how many different numbers are listed are in the new list. So here's our old list above, and here's our new list. And as we look, we have 1, 2, 3. The 9 is also already listed, so there's 3, 4, 5, and then we have the 1/4 is already listed. It's 25/100 is 1/4, so we actually now have 5 numbers. So why do the two lists not have the same number of different numbers? Well, as we talked about just a moment ago, this is a negative times a negative. And so when we get a negative times a negative, our outcome is positive. And what happened here is we know that the output for -3 and +3, when we're squaring the numbers, comes out to the exact same output. The same thing is going on right here with -1/2 and +5/10. They come out with the exact same output as far as a number that has a value. These are, while they look different, they're not different numbers. So why would the two lists not have the same number of numbers? It's because some numbers in the original list namely -3 and 3, and -1/2 and 5/10, when squared, have equal products. And by that I mean with equal products, I mean like -3 and +3 when squared have an equal product, and -1/2 and 5/10 have an equal product. So these inputs, when they have the same outputs, that's what we're going to be looking at when we're talking about functions. We're always going to be looking at the input compared to the output. So let's look and see what a function actually is. We're going to do this by comparing or making some comparison statements. Your job right here is to say yes or no for each question. And do you, like for this one, do you know the height in inches? That's what we're going to be responding to if we know a person is 5 and 5/10 feet tall. If we get a yes, we have to draw the input-output diagram. If we get a no, we need to give examples of 2 different outputs that are possible for the same input. And now this sentence right here, this is where our big information is right here. This is what we're talking about by a function. If the rule does not make sense for the situation, or if the rule can't work, meaning that the rule can't work for all of the inputs and outputs that are out there, then it can't be a function. So as we answer these, as we say yes, that would indicate that there's a function. If we say no, then this is not a function. So this first one, the person is 5.5 feet tall. Do you know the height in inches? Well, of course we do. All we have to do is multiply the height in feet. Whoops. I still didn't spell that right. Height in feet by 12. And so when we write, or write by 12 inches, when we write our input-output diagram, what we would do is we would start with 5 and 5/10. We can draw a little arrow. I'm not going to get as fancy as the ones that we have that they drew with the computer, but we're going to go from here and multiply by 12, to give us our output of 66. And what we can do with this is this function machine would work for any number of feet tall that a person is. All we have to do is have that height in feet and then multiply by 12 and we get the height or the output in inches. Let's look at a few more. For this second one, a number is 5. Do you know its square? Well, of course, on this one, I do know its square, because if the number is 5, then I can take 5 times 5, which is equal to 25. And I can do that with any number that's out there. I can take my number 5 and plug it into my function machine, multiply 5 by itself, and then I get 25. Now, if you think about any number that's out there, I can put any number through this, multiply the number by itself to get 25, to get its squared value. So this isn't unique to just 5. I would just have to change these three numbers, multiply number by itself. Number 3, when I talk about the square of a number is 16. So the square of a number is 16. Do you know that number? In this case, we would have to answer no. It seems like immediately that it would be a yes, but here's our reason for no. There are two different numbers whose square is 16. Namely 4 and -4. And because of that, if we're talking about putting in an input right here of 16 and taking its square, what I would see in that function or in the function is I would see 16 would be having a square root of two different numbers. It could either be +4 or -4. And since the input is just one input, but it has two different outputs, this can't work for a function. So it has to be just one unique output. So, it has to, each input has to be unique to its output. So when we look at the next one, a square has a perimeter of 12 centimeters. Do you know the area? Yes. When we look at a perimeter, the perimeter or the area depends on the perimeter. And so we can say that since it's a square, we know that 12 divided by 4 is 3. And each side must be 3 centimeters, 3 squared. When we take a square, you take length times width is 9. So we know that when we plug that into a function machine, if we take the perimeter of a number, we put it into a function and we find the side length and then square it, we get our output of the perimeter, or excuse me, the area. So put in the perimeter, find the side length, and square it, we get the area. Next one, a rectangle has an area of 16 centimeters squared. Do you know its length? In this case, that's a no. And the reason for it is because we can think of rectangle that has, rectangle A could be 8 centimeters by 2 centimeters, or we can think rectangle B could be 16 centimeters by 1 centimeter. And I suppose you can go and throw in the whole thing about saying a square is a rectangle and go 4 by 4. But the idea is that this area of 16 centimeters does not have one unique output. It's that input of 16 centimeters has different outputs that could be possible. Number 6, you're given a number. Do you know the number that is 1/5 as big? Of course we do. Every single number that we put out there we can multiply it by 1/5 and find it's 1/5 of its value. So when we talk about this, we can simply multiply by 1/5 or divide by 5 to find the number. And so it looks something like this. We take our input, whatever our number is, we put it into our machine, multiply by 1/5, and then our output is going to be 1/5 times the number. or 1/5, that would be more appropriate to put 1/5 of the input. There we go. You're given a number. Do you know its reciprocal? Yes. Remember that the reciprocal is when we take any number and we invert it or make it into a fraction if it's not already written as a fraction, and we invert it. But there's one thing, the number can't be 0. And the reason we can't have 0 is because 0 does not have a reciprocal. And so our machine would look like this. I take my input, any number, and then I divide, divide 1 by the input, which would give me 1 divided by the input. And this is how we would write any reciprocal that's out there. All right, the next step as we look into this, what we're after with this, here's a question from a previous activity, all of the exact same 7 questions. For the ones that we said yes to, we're going to write a statement like the height of a rubber ball bounces to, or the height a rubber ball bounces to, meaning how tall it bounces, depends on the height it was dropped from. Or the bounce height is a function of the drop height, meaning that the bounce height is dependent on the drop height. So for all the ones that you said no to, we're going to write a statement like the day of the week does not determine the temperature of that day, or the temperature of the day is not a function of the day of the week, meaning that the temperature of the day does not depend on the week that's there. So a person is 5.5 feet tall. This was a yes. And so what we would understand with this is that the height in feet depends, not height in feet, the height in inches depends on the height in feet. I guess this could go either way around. The height in feet does depend on the inches. We could see that in both directions because it's both unique outcomes. Does the number, or a number is 5? Do you know its square? Yes. The square of a number depends on the number itself. So the output with this, right, if we're talking about the square, if I'm saying some number squared is equal to 25, then I know that the number right here, n, must be 5. I know the square, right? Or maybe I could say something like this. A number is 5. Do you know its square? I think that would be a better representation. We sure do know its square. So a number squared is this. It all depends on understanding what that base is right there. If you know the base, you're good to go. So how about this? The square of a number is 16. In this case, remember how this one had the output with it? We said that we could have 4 and -4. What that means is that this is a no statement. And the reason for that is because knowing the square of the number does not actually determine the number. So knowing the square does not determine the number. Now, what does that mean? Well, it means that just because you know the square of the number, that's not what makes the square of the number. The square of the number is made by the original input or the base that was given. This is an output. The square of a number is an output. And the output is never dependent on the input. Wait a minute. The output is always dependent on the input. You can't put this one as an input because this is an output. And so it actually would simply not work as a function because we're claiming that the output is dependent, or excuse me, that the input that we give is dependent on the output. And that's just not true. When we talk about the square perimeter is 12 centimeters, this is a yes. Do you know the area? Well, area is dependent on the length of a square. So area of a square is dependent on side lengths. You have to know the side lengths in order to determine the area. Number 5, a rectangle has an area of 16 centimeters. Do you know its length? No, because of what we talked about, knowing the area. Just because we know the area does not determine the length of one side. So we have to know the side lengths in order to know the area. Just because you know the area doesn't mean you know the sides. And again, in this case, we know that the area or the side lengths of that rectangle could be an 8x2, it could be a 4x4, it could be a 1x16. And if we don't know any of those things, there's a huge amount of possibilities that could happen here. So if we're given a number, do you know the number that is 1/5 as big? Yes. Every number getting a little wild with my writing, sorry about that. Every number determines 1/5 of a number or of another number. So when we're talking about that product that's 1/5 as big, that one's going to be the number that's dependent on the other number that we're given. So if we're given a number, do you know it's reciprocal? Yes, as long as it's non-zero, right? I think we could say every non-zero number determines its reciprocal. Okay, sorry for any confusion that was in there, but the biggest thing is this. When we're talking about a function, is the output dependent on the input? And if we could flip it around, are we saying that the input can never be dependent on the output? So we're always having to think in terms of how are we going to find that output and how does that output relate to the input as far as the relation of dependency. So here's a good example of this when we talk about it. And when we look at these 3 function rules, are any of these function rules, which input-output rules could describe the same function, if any? Be prepared to explain. We have 7 being squared, so we take any number, square it, and we get its output. We take a number, we find the area given the side length. So if we know the side length, if this would be a side length, and then we square it, this would have to be the perimeter. And then down here, we just have any number and we add 90 to it to get 100. Now, I think that the one that might be the one that stands out as the obvious answer would be these two, would be the two that represent the same function, but there's a key difference between them. This function right here is showing addition of 90. So if I changed my number right here to 20 and then I add 90, then I get 110. If I change it to 30, then I get 120. Whereas in these ones right up here, if I find the area of a square or of a length, if I take this one, change it to 9, I get 81. In this case, I change it to 9 and square it, I get 81. If my perimeter was 7, find the area given the side length, then I take my area is always going to be side length squared, side length times side length, which is going to be 49. So what we actually see is these top two are the ones that represent the same function. And the reason behind it is because they're both operating in the same bounds. They're both using multiplication and they're both squaring the input. So this one, we could just say the input is squared. We could also say this one, that the area given is the side, or given the side length, I can find area by multiplying the side length by itself. This case, there's no multiplication, so these two values cannot describe each other. Or excuse me, so this function is not describing the same thing as these other two functions. Whew. Okay, that was a lot to give you. It still leaves functions a little bit ambiguous. We're going to see some more information about functions in the next lesson. But for right now, what we need to know is that if we have an input-output rule, for each allowable input gives exactly one output. So when we're talking about this, we get each input. I guess the main concept is that if we're going to have a function, we can only have each of the inputs attached to its own unique output. We can't have an input that's going to two different numbers. We're going to see that in the next couple lessons, but we say that the output, this is the key thing, output depends on the input. That's the big key. Output is a function of the input, meaning that output doesn't happen without the input. We can't say it the other way around. Input depends on the output. So for example, the area of a square of a function of the side length that the area of a square is a function of the side length because you can find the area from the side lengths by squaring it. So when you put in 100 centimeters, the output is going to be, put in 10 centimeters, the output's 100 centimeters square. Sometimes we might have two different rules that describe the same function, and as long as we always get the same single output from the same input, then the rule describes the same function, such as this one right here. With this one, we really can't flip it around and say that the side length gives us the area of a square. That the perimeter gives us the area. We have to be able to understand that the input or that the output has to depend on the input. I better just quit now. Thank you for your time, and hope you have a great day. Check in with me if you have some questions.